Today we'll begin sampling and estimation, the final chapter in the methods course. It's pretty new, so it came about in 2016, so you won't see it in any old VCA or trial company papers pre-2016, and it does a really nice job of bringing together discrete and continuous probability. So let's have a look at it, starting with populations and samples, and we're going to look at the difference between these two things. So it's a fact that people hate to waste time doing unnecessary work, and one thing statistics can do is tell us exactly how lazy we can be. So imagine you're attempting to find the average length of a pickle. That's the question we've got. So we could measure every single pickle, that's what we call the population in the world, and do some arithmetic. You understand that the practicality of that is zero. Okay, we're not going to find every single pickle in the world. And we're I can't even say the word, but we're statisticians, and we are looking for the easy way out. So what we do is we would take a sample, a small subset of the total population. So the population can be defined as including all people or items with the characteristic one wishes to understand, and there's some notation involved with this. So the number of members in a sample size, n, and the number of members in the population is called the population size, and that's capital N. And sometimes we actually don't know what the population size is. We do know what the sample size is because we take a sample of 700 or 200 or 10 or 15 or whatever it is. But sometimes we don't know the population size, and this is a classic example. Okay, if we're measuring every single pickle in the world, and then you ask me, well, hey, how many pickles are there? It's like, I wouldn't have a clue. Millions? I don't know. Okay, so here's an example. Cameron has uploaded a popular YouTube video. He thinks that the 133 people in his year group at school have seen it, and he wants to know what they think. He decides to question 10 people, identify the population and the sample size. So the population, so capital N, is equal to 133. They're all the people in his year group, okay? So just noting that the population isn't every single human in the world when we're talking about this, it's just the people in his year group, okay? And to work out whether they've watched his video, whatever it is, I don't know what Cameron's doing. My son seems to like Minecraft videos, so maybe Cameron's doing Minecraft stuff. Anyway, what he does is he asks 10 people. So this is lowercase n, that's the sample size, okay? So lowercase n equals 10. All right, so when we're taking a sample, we do this thing called a simple random sample, or SRS. So the principal way to guarantee that that sample data will be representative of the population is to use simple random sample from the population. So what is it? With a simple random sample, every conceivable group of units of the required size from the population has the same chance to be the selected sample. So that means that of the 133 people in, who was it, Cameron, was it? In Cameron's year group, every one of them has the same chance of being selected in that 10 that he chooses as a sample, okay? So it's important to note that Cameron can't simply wait out the door of a classroom of, say, accounting students and ask the first 10 that come through. That would not be considered a simple random sample, okay? So what he has to do is use a method to ensure that these 10 people selected are or have exactly the same chance of being selected as all 133 people in his year group. So we do this when we're taking surveys or polls, okay? We make sure that everyone has exactly the same chance of being selected. So we can select random numbers on our calculator, and here's the method to do it. So I'll just step you through it. So what we do, go into main and keyboard, we go into this advanced section. What we want is to draw from the catalog the rand functions. Okay, so it's under R for rand. And the first one is just a straight up rand. All right, now what it does is it allows us then to generate a random number. Okay, so all we do is we put in the lower bound and the upper bound and hit enter, and it selects a random number between 0 and 1. This time it selected 1. Now it's selected 0, 1, 1 again. Okay, and this is random every time. We can select a random number as this suggests, from 1 to 6, 4 first of all, so simulating a dice roll would be 1 to 6, etc, etc. Okay, and this method here would be completely free from bias. Okay, so we're just noting that there's no, or every number between 1 and 6 inclusive of 1 and 6 has an equal chance of being selected. Sometimes you might think, oh, couldn't you just get a human to spit out some random numbers? Just go to your mate, hey, give me a random number between 1 and 6. So let's presume that your mate is the random number generator, and they give you the number 4. Okay. Now the number that I just chose in theory at random actually is not random. And here's a really good video by what was his name, Simon Pampina, from the Numberphile series, where he goes through and actually wins a whole heap of money on the basis that someone picks a whole heap of random numbers, or random coin toss results actually. So we're not good at generating them. That's why we need the calculator to be able to do this for us, is it does not select random numbers based on some sort of information or bias or anything like that. Alright, and the calc will also generate a random list of numbers, so you can just use the rand list. And the way rand list works is it looks for how many arguments? I think it's 3 arguments. Okay, so the first argument is the number of random numbers, so for example 5 random numbers, and the last 2 is what it wants it between, so 1 and 6. So this will generate 5 numbers between 1 and 6, or simulate 5 rolls of the dice, and there they are. Okay, you just need to note to be careful, as this will list repeated numbers. Okay, so you can see here that 2 comes up twice and 1 comes up twice. That can happen with a dice roll. We all know that you can roll 6 times in a row. If it should happen, it's a possibility. Unlikely, but it can happen. Okay, so let's have a look at this. So the population versus sample proportions. Okay, so now we're really getting into this unit. So the population proportion is denoted by a lowercase p. So suppose the population of interest is the students at Sacré-Cœur, and that we were interested in the proportion of those who play an instrument at Sacré-Cœur. This is called the population proportion and is denoted by p. So remember, what we're talking about here is all students at Sacré-Cœur. So this value remains fixed and constant for a particular population. Okay, so this is how we work it out. The population proportion, or P, is the number in the population with the attribute and the population size. So let's suppose that 356 play an instrument of the, let's presume it's 635, I don't know what it is at last count. Therefore, our population proportion is 356 out of 635. Okay, so P will always be between 0 and 1. Okay, so a value between 0 and 1. Could it include the endpoints? I suppose it can. Yeah, it definitely can include the endpoints, although yeah, I suppose that would presume that of the 635 students, 0 play an instrument. So 0 out of 635, or 635 out of 635. So P can be any value between 0 and 1 inclusive of that. So again, it's important to note that this is always constant. This will always be our population proportion. And let's take this class as a sample of the population. Are we representative of the entire population? So we know that there's 13 of us, okay? And I'm going to say, and I'm going to make this up, that for argument's sake, let's just say that 4 out of 13 play a musical instrument. So let's have a look and compare on our calculator. So 4 out of 13 is that. 356, well, it's not going to be close, is 0.56. So we're going to conclude, no, we are not representative in this case. All right, so here's the fundamental rule for data, for using data for inference. Inference, which means making or inferring, making predictions on. So is that the available data can be used to make inferences about a much larger group if the data can be considered to be representative with regard to the questions of interest. Okay, so that means that of the sample, or when we look at the sample, it needs to be representative of the population. So for the purposes of this example, let's say that we are representative. The sample proportion is denoted by this thing with, it's a P with this, well, hat on it, and we call it P hat. Literally, we call that P hat. So the sample proportion, P hat, is the number in the sample with the attribute, which in our case we made up that, it's 4, over the sample size, which is 13. And P hat will vary from sample to sample. For example, we might have Ms. Carroll's class, okay, and she might find that they're just a particularly a musical class, so they might be 7 out of 13. Okay, so we notice that the sample number in the sample with the attribute in her class is 7. Okay, the number in mine is 4. So this varies. Okay, so the number in the sample with the attribute will vary from sample to sample depending on who's being sampled. You know, you ask a year 7 class, okay, my year 7 class, you know how when you're young you want to try everything out, and like, you know, they might be 17 out of 19 students who play an instrument. So here's how it looks pictorially. Okay, so this is the entire population here. Okay, so it's size N, okay, and capital N in this case. And the population proportion is going to be 1, 2, 3, 4, 5 out of a total number here. Just going to pause this and not count it while you're watching. So there was 29 there. So that means that P is equal to that. So this is the population proportion. Okay, now this one here, we're going to get P hat. This is the sample proportion, okay? And what we can see is that P hat is equal to 1 out of the sample, which is 1, 2, 3, 4, 5, 6, 1/6. Okay, now again, this number here will vary depending on the sample taken. Okay, so I might get 3 of these from from out of a sample of 6. So this could be 1, 2, 3, 4, or 5 in this case. Yeah, we don't know. All right. So since P hat varies from sample to sample, we can consider that the sample proportion P hat as being the values of a random variable, which we denote by capital P hat. So this is capital P hat. And this is exactly what we've done for random variables in probability all the way through. So we start to link up with some of your prior knowledge. Right, so let's just do a couple of examples to get you through 17A. In a certain school, 35% of the students travel on the school bus. A group of 100 students were selected in a random sample and 42 of them travel on the school bus. In this example, what is the population? Well, it's all students at the school. In this case, we don't know how many students they are. It doesn't say. What is the value of the population proportion? Now we do know that because they tell us that 35% of the students travel on the school bus. So the population proportion is 35 over 100, which is 7 over, what's that? 20, mental blank there, or just 0.35. It doesn't have to be a fraction. You can write it as a decimal. And then let's have a look at the sample proportion. So this is P hat. Okay, so P hat in this case is going to be the number of them identified, which is 42, of the sample, which is 100. So that's 21 on 50. So P hat is 21 on 50. Or another way of thinking about it is 0.42. Okay, so noting that it's not the same as the population proportion, nor would we expect it to be exactly the same every single time. Okay. From 60 samples of 30 people, each are chosen at random to see if they are right-handed. A total of 162 people are left-handed. Find the expected sample proportion of being right-handed, correct to 2 decimal places. Okay, so a bit of number crunching has to go in here. So we've got 60 samples of 30 people. So we're going to do 60 times 30. What's that? 1800. So 1,800 people are surveyed at random to see if they are right-handed. A total of 162 people are left-handed. So find the expected sample proportion of being right-handed, correct to 2 decimal places. Okay, so that is the sample proportion, p hat, which, remember the formula, it is the number of people who exhibit this thing here. So right-handers, which is 1,800, take away the number of left-handers, which is 162, over the number of people that are in the sample, which is 1,800. So probably can do this without the calc, but let's just use it. 162. So that's 1,638 over 1,800, which is then 0.91. As a fraction, it would be 91 on 100. Oh gosh, I can't believe I had to do that on the calculator. That's embarrassing. Anyway, I'll leave that in there. All right, so your exercise is 17A. All right, and you will tear through that really, really quickly. So go for it.